to find volume under the surface, z equals 2x plus y squared, and above the region bound by x equals y squared and x equals y cubed. So, notice that in this one, the bounds are very different. Included in your notes there, you see that the swap, in order to swap the dx and the dy, the bounds do a really odd swap too. Notice that if you solve x equals y squared, you'll get the square root of x is equal to y. That's the swap happening on those bounds. Does everybody see on the notes what I'm talking about in the bottom right here underneath the picture? Notice that the bounds are swapping. And the bounds are more complicated this time because we're looking for the intersection of these two lines. The same way as when you used to calculate the area between two curves. Right, if I ask you to find the area between these two curves, let me draw this slightly differently. You'll find this intersection and this intersection. Well, these are where these two lines meet. One of these lines gives us the intersection x equals y squared, and the other one gives us the intersection x equals y cubed in this case. So when we go to do this double integral, it's not very bad. It's not very bad because the thing I have to integrate here isn't too terrible. So I'm going to integrate this with respect to x. The integral of 2x with respect to x is x squared. The integral of y squared with respect to x is x y squared. This is evaluated from y cubed to y squared. Yes, sir.
Isn't a typo in the packet that these are switched in the other example? I mean, in the next part of it, where she changes it from x squared, y cubed to y squared, is what I'm saying making sense.
Are you talking about the bounds, where the bounds
Yeah,
go
for the
with x
bounds
squared?
change for the second one, like she switches it.
No, there's no typo here.
Okay.
What you're not, look at the end there. One of them is dx dy, the other one is dy dx.
Yes.
And so that swap in bounds means you have to solve these the other way, right? Where does x go from? X goes now not from, where x went from y cubed to y squared,
Okay.
y then would go from the cubed root of x to the square root of x.
Okay.
Yes, ma'am.
Okay. Well, I'm still not getting that. I get how you, I mean, you kind of just explained that, but I understand like how you get them when you put y squared in terms of x, how you solve for that. But it's still confusing why when you're solving for y squared in terms for square root of x, why wouldn't that square root of x just go at the top? Be the upper bound.
Because if you look at the, so she gives you a picture of the slice of intersection happening there, right? The upper intersection is not necessarily the leftmost intersection. Right, if I have a picture that looks like this, in this case, if I'm going left to right, it's this bound to this bound. And it's also, if I'm going up to down, it'll be this first one followed by that one. But if the intersection looked like this, and I'm going left to right, it's this intersection to that intersection, and up to down, it's this intersection to that intersection. So that's why those two are also being swapped.
Okay.
For that, you really have to look at the image that she's put there. There's really no way other than seeing that or evaluating it and seeing if numbers are smaller or larger to know that you need to do that swap. And you guys also know if you swap those two, you'll just be assigning the wrong sign to it. You saw that from your Calc 2, I think, being Calc 2. So, need to evaluate this from y squared to y cubed.
That last one should be a fifth, I think.
Yep, thank you. So, this is now the integral, 0 to 1, y to the fourth, 2y to the fourth, minus y to the fifth, minus y to the sixth, dy. Is equal to y to the fifth, 2/5, minus y to the sixth, over 6, minus y to the 7, over 7. Evaluated from 0 to 1. This is 2/5 minus 1 minus 1. Well, I did that way too fast. 1/6,
Yeah.
1/7. Pull out my handy dandy calculator.